Hi, Laurie.
Hi, Cyrille. How's it
How are you?
going?
Good, and you?
Not too bad.
Yeah, I didn't refer to your email yet. Yes, Tom will serve someday. I hope this summer. Yeah. Profile posting. Yeah, I have to adapt with the seasons.
That's good. He looks very comfortable in the snow.
Yeah, he really loves it. Yeah. He said he was really proud to ski. We asked him, you know, are you proud of you? You did well, and he was like, Tom is proud. In French, not in English yet.
Yeah. Make sure he gets the English sorted out.
Yeah, with a better accent than me because he's American, so it would be a shame.
People are still joining, so we'll wait just probably one more minute and then get started.
Perfect.
All right, well, people are still joining, but we don't want to let the time get away from us. Welcome everybody to our weekly seminar. Today we have the pleasure of hosting Cyrille Mosbeux. I'll be introducing him, but before I do, just a quick reminder to make sure that you are muted for the duration of the talk until Cyrille is finished, and then of course we'll open up the floor for questions. So Cyrille is originally from Belgium. He studied mining and mineral engineering at the University of Liège in Belgium. He received a doctorate at the Insitu Polytechnique de Grenoble, studying processes responsible for the acceleration of outlet glaciers using inverse methods. He was then a postdoctoral scholar here at Scripps for a while and has recently moved back to the University of Grenoble in France, where he is a researcher at the Institut de Géosciences de l'Environnement. He is a part of two European projects, TPAX, which assesses the possibility of near future irreversible changes, so-called tipping points in the Southern Ocean and the Antarctic Ice Sheet, and PROTECT, which assesses and changes in land-based cryosphere with quantified uncertainties to produce robust global, regional, and local projections of sea level rise on a range of timescales. So I think it's a pretty good idea that today we'll be hearing about ice and its relation to climate change, in particular the Ross Ice Shelf. And without further ado, Cyrille, the floor is yours.
Thank you. So yes, as you just said, I want to take you on a journey into the icy land of Ross Ice Shelf. It's a journey in mind, of course, but yeah, it's also a walk I did and a journey I did with many people learning about Ross Ice Shelf. especially Emily Klein and Peter Brinsky and Yehuda Bock and Maya Baker from Scripps, but also Scott Springer and Till Wagner. So Scott Springer from ESR, and Till Wagner was also a postdoc at Scripps, and now he's a professor at assistant professor, sorry, at the University of Madison. And then of course Helen Fricker, who was my advisor at Scripps, and Laurie Badman. He works a lot with Helen, and they were like both a very good support to my work in general. Oh, I can't. Oh yeah. Okay, so the first question we can ask is like, why studying ice and why studying Antarctica in general? And you can have one answer looking at this video from Gray's observations. So you can see that the ice sheet, the Antarctic ice sheet, is losing mass in some areas, and especially in some sectors like the Amundsen Sea sector. So you see like those really dark red colors, meaning that the ice that Antarctica is losing mass in those areas, and other areas that are actually much more stable. And you can see that the general mass loss is like, you have an increase in mass loss over time during the two last decades. And so this was from Gray's satellite, but you can see the same looking at ISAT-1 and ISAT-2 ice thickness change measurements for, again, the last 2 decades, more or less. You have the same patterns with the Amundsen Sea, which is very unstable, like losing a lot of mass, and the Ross Ice Shelf, which is again pretty stable. And this is directly linked to the basal rate you can observe. So here it's a paper from Sushil from Scripps too. Using cryosat, you can reconstruct basal rates. And you can see that in the Amundsen Sea sector, we have large basal rates, which are linked to a strong thermal forcing, while on Ross Sea, the thermal forcing is much cooler, and the Ross Ice Shelf is much more stable. So with observation satellites or tide gauge, you can measure the sea level, and you can also measure the contribution of Antarctica to sea level change during the last 100 years or even more. But you can't really predict the future. So you need for that computing model, you need numerical models. And you can apply some forcing, some climate scenarios to the ice sheet and see what will happen in the future. And you can see that depending of the scenario we look at, like large emission in red, or light emission of CO2 and light warming, will have a different sea level rise, and then a different contribution of Antarctica to sea level. Okay, so this is why we study ice most of the time. There are like a lot of other interesting questions, but this is the big question we try to answer in general. It doesn't really explain you how do we describe the ice flow in general. And like for a river, you know that we have to use fluid mechanics to solve a river problem, like how the river can flow, for example. And for that, you use Navier-Stokes equations. And because ice is so viscous, you can delete some terms from this equation. And you can also consider that the ice is incompressible, that the density of the ice is kind of constant over time and space. So you can delete some terms from the equation, and you end up with a glacier movement, like a Stokes equation. It's the Stokes equation, this simplification. And you can compute the flow of ice. And for that, you use those two equations, but also the link between the stress in the ice and the velocity that is linked to the stress. So you apply a stress and you compute a velocity in the ice. And you can link the stress to velocity and to strain rate with the nonlinear relation I show you here in the center, where you can see that the stress, the deviating stress, is linked to strain rate and to viscosity. Viscosity, which is again nonlinearly dependent on the strain rate. So it's a complex system to solve, but we can do it. and sometimes, because it's numerically expensive to do that, ice sheet modelers, they use some approximation of these equations to have a more efficient code. And yeah, so that's how ice flows, but we want also, you know, to explain how the entire system works, and we want to represent the entire system in the model. So for that, you need atmospheric forcing, which is for ice sheet, basically the surface melt or the snowfall. You need also to know what's the geometry of the ice sheet, how does it lie on the bedrock, for example, what's the basal friction you have beneath the ice and between the ice and the bedrock, the hydrology. You also need to know what's happening at the ocean ice interface. So basically, the ice sheet is flowing on the bedrock, but at some point it goes afloat when it reaches the ocean, and you have some melting on those ice shelves that are floating on the ocean. And then the ice shelf extend, and it ends up calving, because if there was no calving, it would just extend forever. So this is basically the system we try to represent, and there are like a lot of simplification, because this is the global and entire system, but a computer is usually unable to solve all of it together. So as I said, I want to take you on a journey. So we will start our journey from Scripps Institution of Oceanography, where most of you are right now. And yeah, we will travel to Ross Ice Shelf in Antarctica. And we arrived in the McMurdo station here. You can see it's a rocky, it's kind of a rocky island surrounded with ice, and all the ice you can see is the ice shelf surrounding the island, and also the ocean. And it's a Google Earth animation, so you can see also that it's pretty bad in terms of imagery, but yeah, you have the idea. And this is the McMurdo station. Here you see again the ice shelf in the background, very flat ice. And well, why do I take you to Ross Ice Shelf? Because as I said, it's a pretty stable ice shelf, right? It's not melting that much. The ice mass is kind of constant. So why do we care about it? And so for the Rosetta project, we have studied Ross Ice Shelf, and we have studied the basal melt rate of Ross Ice Shelf, and we try to reconstruct in a paper from Indranidas to reconstruct the basal melt rate over a few last decades, about 10 to 60 years. And you can see that this basal melt rate is very consistent with the observations you can have in Adusumidi, so in Sushil's paper in 2020, based on satellite and Cryosat-2 to be exact. So you can see that the basal melt rate didn't change didn't change that much over the last decades. So could be said as a boring place, right? But actually it helped us looking at smaller changes in the ice shelves and the ice sheet. So in a paper we had in 2019, led by Kirsty Tinter from Lamont, we reconstruct a completely new bathymetry of the ice shelf, beneath the ice shelf. And we ran an ocean model, and we tried to reconstruct and to compute the melt rate, the circulation of the ocean and the resulting melt rate beneath the ice shelf. And this is what you have in summer. You can see a very large, very, very important melt at the front of the ice shelf, and also in a small corridor here. Here you have Ross Island, where you have the McMurdo station. And actually, what is really interesting is that this paper really agrees with another one that came in the same time from another group, and totally unrelated, because this is based on Apiray's observation. Basically, they show the same melt in summer with respect to the rest of the year. So there is a peak in melt, and they asked the question, okay, maybe Ross Ice Shelf is stable right now, but this kind of melt, does it matter for the future of the ice shelf? For example, if the summer was to be more was to last longer, or was to be like more important, you know, like even more melt than what we see right now. So this was a question. And in the meantime, Peter Bomirski and Nick Lane and Yehuda, they came to us asking about something they saw on GPS observations. So they had this trend in the GPS observations on the ice shelf. Here you can see the different GPS, and you can see a negative trend with an along flow displacement, a negative along flow displacement during summer, and then a positive trend in winter. And they asked us, okay, what's the cause for this? And the first idea was maybe it's sea ice, you know, sea ice pushing. You have sea ice in winter, so it pushes the ice shelf back inland. And when you have no sea ice, then the ice can flow faster. But it was not really a good explanation, because the sea ice there, concentration there is not so high, and also the layer of sea ice is so small that we doubt that it could really cause such a change in the ice flow. So another idea was melting, and it's directly related to what I told to you about just before. So because we have high melt in summer, maybe it's able to, you know, change the ice flow during the period, and then the flow is going back to normal after the peak in melt. So what we did is to use Scott Springer model with and from Tinto et al. 2019. You can see here 3 different type of water, but we are really interested in the Antarctic surface warm water here, where you can see that in February, which is summer in Antarctica, you have a pike, you know, in the tracer of the Antarctic surface warm water, and you have like a linked high melt to this intrusion of water in the cavity. So this intrusion is due to the fact that in summer you have no sea ice, and the surface water can warm and enter the cavity and melt the ice. So when we use this model to compute melt rate, for example, between January and February, we can see an increase in melt rate, like we have on the left figure. And on the right, we can see what happens when we apply this melt to an ice sheet model. And basically, because we melt, we reduce the ice thickness, and we start to accelerate. And in winter, it's the opposite. The melt decrease and the ice shelf is decelerating. So it's a good pattern, because it's more or less what we wanted to see. And what we wanted to reproduce. So what you see again is a high melt in summer. You have the peak in the red curve in the first panel. So the melt rate is peaking, and then this is directly linked to sea ice. No sea ice concentration. So you have the ocean warming, and then that's in the third panel you have the model response to this melting and the observations. And you see the curves are pretty well aligned. The only problem is that the amplitude of the signal is completely different. It's about 30 centimeters of variation when you look at the model, while it's a few meters of variation when you look at the observations. So melt is a factor, but it's not enough. So the question was, again, what could cause such seasonality if it's not the melt? And after our first study, we came with this new idea, and also some new observations, new GPS stations that we didn't get during the first study. And we thought about a mechanism, which is the effect of sea surface 8 on the ice shelf. And so if you take the ice shelf system and the flow computation as the F function here, and you have the basal drag, which is the drag on the of the water on the ice shelf, which is basically 0 here, and the driving stress. You can think about the link between the driving stress and the velocity, and the driving stress is basically a function of the surface slope of the ice shelf. So if the surface slope increase or decrease, you change the flow. And when you have sea surface height variations over the year, so you have here you have a flat sea level, and you think about the variation of the sea level due to the variation in sea surface height, you start to, and that the ice shelf respond hydrostatically to this, you have an increase or a decrease in the driving stress and a change in the flow of the ice. So in summer, for example, if you tilt the ice shelf, so if the ice shelf is tilting, it's slowing down, and if it's tilting down, it's accelerating. And another mechanism is the growing line migration. So basically, what we think is that because of the change in sea surface height, the growing line, so the line between that separates the grounded ice to the floating ice, changes. So the grounded ice is retreating inland because it's, the ice shelf is just like going up or going down. So it lies more or less on the bedrock, and this changed the friction in the grounding zone. So the thing is that to study this, we need to know what is the sea surface height beneath the ice shelf. And the problem is that with observations like Cryosat-2, we don't have any idea of what's happening beneath the ice shelf. We have an idea of what's happening in the open continental shelf and the deep Ross Sea, for example, because we only have sea ice, and we can have a signal there, but nothing else beneath the ice shelf. But what we can do is to use ocean models like METROMS or NEMO. Here you have two different simulations, and you can look at, okay, do they look like the observations? And the answer is not really. For example, you can see here that when you take the average sea surface height variation over the years between 2011 and 2017, you can see that sometimes the model agrees with, like NEMO, agrees well with the cryosat observation. So the two green boxes are very well aligned, but the red box is not the same as the other two. So, and sometimes the opposite, like METROMS works and NEMO doesn't. So those models don't really work well. So it's hard to know exactly what's happening beneath the ice shelf again. But we had a third model. It's again the RUMS model from Tinto et al. 2019, where you can see that we have very similar pattern between the Cryosat-2 data and the model. So you have basically negative sea surface height during the first part of the year, January, March, and then it's going to sorry, it's the opposite. Yeah, it's a negative, then it's going positive. The color bar is reversed here. Sorry, and then again you go to a negative anomaly. So when you compare those two, you see a peak correlation of 0.94. So it's really well correlated, and we went with this model to look at the impact of sea surface height change on the ice shelf flow. And what you need also to include, in addition to the sea surface height change that changes the ice shelf, as I said before, is the growing line migration. And the growing line migration can be seen as an hydrostatic system, but usually it's actually not really hydrostatic. And some study, I will not go into the details here, but some study show that it's not the case. And that actually growing line migration could be larger than what gives the hydrostatic migration. So it means that if it's larger, the growing line retreats more or less. So the friction in the grounding zone change more than in the hydrostatic case, so you will have more impact on the ice flow. So in our modeling study, we tried 3 parameterization. One is the hydrostatic parameterization, and 2 others are based on some theories based on elastic track mechanics from other researcher, actually Tsai Gudmundsson 2015. And what we end up with applying those 3 parameterization in our ice sheet model is that we are able to reproduce better the ice flow variation. So the ice flow variation in the model are closer to what we observe on the GPS station. So on the left panel, you can see the trend. It's a kind of a seasonal signal, or at least intra-annual signal, with a slowdown of the ice shelf during January, March, and then an acceleration of the ice shelf from April to September, and then the velocity going down again. And this is exactly what we see on the right panel when we compare the observations in green and the different models. And yes, the gray model, which is the small growing line variation, is not working that well, but the two others are working well. So it means that we need this non-hydrostatic growing line migration mechanism. It's a question: is it real or not? But when we apply it, it works pretty well. So it's a good news, because it means that C-surface 8 might be the mechanism we were looking at for so long. So now I want to bring you to another part of Earth's ice shelf. We looked, at GPS stations over the ice shelf. We looked at the front. Now we will go all over the front. So we will follow the front of Earth's ice shelf from the Ross base to the completely opposite side of the front. So you can see Ross ice shelf front here. It's a very long front. It's about, like, I would say 800 kilometers, maybe. I'm not sure of what I say, but yes, something like that. And you can see in Maya Baker's work from 2000, so it's a paper she published in 2021. She was a student with Helen, and you can see that along this front we have some weird shape. So this is like some tracks from a GPS, from some track from altimetry, and on the lower panel you can see a number going from 0 to 20, which is actually a number giving you how the front is rising right at the front of the ice shelf. So the ice shelf is going down, and then right at the front we have a rampart that elevates for a few meters. So this is the mechanism we think is happening here. So basically, you have an ice shelf, and at some point you start to melt more at the surface of the front than below the water, because you have warm ocean water there, and you have also the erosion of the waves. So you leave an underwater foot below the surface water, and you create a rampart because you have extra buoyancy, so the ice shelf starts to bend, and you create what's called a moat, which is the moat of the rampart moat, and then the rampart going up. So just a video to show you what we think happened, and actually there are like some proofs of this, not for Ross ice shelf, but for other ice shelves, for other parts of other glaciers. So this is what happens, and one of the questions we had is, okay, is it viscous or is it an elastic process? The ice shelf goes up like directly, you lose ice and you go up, or it's a process that takes time. And so we, in our study, we investigated this, but before really going into the details of the viscous versus elastic study, how do we know that there is a foot? And as I said, for a ice shelf, we don't really know. But you have here a paper from 2014 where Till Wagner worked on an ice shelf, an iceberg flowing from Petermann Glacier to the Baffin Bay. And in the Baffin Bay, you can see the location of the iceberg in orange. They just measured the footprint of the ice shelf below and above the surface of the water, and you can see the presence of the foot, which is directly linked to a temperature change in the water. So at the surface you have warm water, so you melt more, and then you leave the foot because the ice is melting less at depth. And as I said, we have no proof of that for Ross ice shelf, but if you compare an iceberg from Baffin Bay in 2012 to an iceberg photo of in the fast ice off Ross Island in 2019, we see a really similar shape. And if you take this little piece of ice, this iceberg, and you think about his position in the ice shelf, at the front of the ice shelf, you can basically reconstruct what the front of the ice shelf looks like. And indeed, it looks like we have this foot. So people have worked on this buoyancy stress effect before us. Till Wagner, he worked on a 1D elastic model to try to reproduce the curve of the ice sheet, so of the ice shelf at the front, so the rampart and the moat. So he used an elastic model for that, and he tried to fit with an elastic model what we could see, what we could observe. And using the same model for our Ross ice shelf, we can see that we are able to reproduce the same shape. But this gives you a shape, but it doesn't give you what happens in terms of mechanics and stress, because what we want to know is this kind of shape able to lead to a calving? Because when you have this shape, you bend, you create an extension stress at the base of the ice shelf because of the bending, and you can if you have enough stress, if it's bending enough, then you can calve. So we want to know what's the impact of such feature on calving. And yes, for their 1D modeling, they needed to use a very large range of elastic models. So the elasticity of the ice was very different from one case to another. So it's a parameter we have to fit every time, which complexified the results of this kind of study. So it's an interesting thing, because I tried to make a link with what other people do at IGPP, and especially Dave Sandwell. So what we do here in terms of fitting a curve, fitting a surface with an elastic model. Actually, Dave Sandwell and his group, they worked on that also, and I guess a lot of other people work on that. So they work on that to fit a seafloor topography. So they use exactly the same principle, for example. So it's interesting to see how ice sheet modeling and calving, whatever, like Antarctic science, they can be linked to other sciences. And yes, so just to show you what happens in the system here, you can see a nice track here, and you can see how the front of the ice shelf is creating a rampart, and then the rampart is disappearing because basically we think we have a calving event. And this happens over a time scale of 1 to 4 years. So it's pretty long. And the question is, okay, as I said, most of the time we treat ice as viscous. And now Till Wagner, he worked on ice as other people. He worked on ice using an elastic model. So does it make sense? What is it? Is it viscous? Is it elastic? For a viscous model, for an elastic model, 4 years looks pretty long. So is it realistic, or should we use a viscous model? And more important, if we use one or the other, what's the implication for calving events? So just to make you realize, so if we talk about elastic model or viscous model, elastic or viscous is the same principle. It comes from Newton's law, right? And then the big question is that the big difference is that for viscous stress, the stress is linked to the strain rate, while for an elastic stress, the stress is directly linked to the strain and to the Young modulus, for example. And for a viscous fluid, more fluid, because it's warmer, it will deform more or faster. While for an elastic model, it's the rigidity of the ice which is linked to the Young models that really matters. But in the two cases, the stress you can apply to the maximal stress you can apply to ice is similar, and it's 1 megapascal. So just remind, people have worked on ice as viscous, people have worked with ice as elastic, and the question is, in this particular case, what does it change? And here you have a 2D viscous model and a 2D elastic model of an ice shelf. With different size of foot. So in the first line, you have no foot, and then you increase the size of the foot, and you look at what happens in terms of stress distribution when it's viscous or elastic. And when you look at the elastic stress, it's just instantaneous. So it's just like bam, it responds. But when you look at the viscous model, it takes time. So here it's like after just less than a day, like a few hours, you have the viscous stress is like that, and then it's changing, and it's the ice shelf is deforming, the rampart is rising, and the stress is moving forward. The maximal stress is moving forward. So if you look at the stress distribution, it will depend on the framework you use. If it's an elastic framework or viscous framework, your stress will be position, your maximal stress position will be different. So you can see on the left, we try to have a rampart mode, elevation and shape that are very similar. But in the end, on the right panel, you can see that if you take the plane line and the dash line, which is the elastic and the viscous model, you can see that the shape of the stress is different, and the maximal stress is different, position is different, which means that if it has to calve at some point, the maximal stress is at a different location. So the calving position will be probably at a different position. So you will create a larger or a smaller iceberg depending on the framework you work with. So sure, there is a difference between elastic and viscous, but here it's for one case of viscosity, so it's for one temperature. So what's the effect of temperature? If we change the temperature in the ice shelf, the viscous model will maybe respond differently, and this will change the stress distribution. So here you can see on the left the curves we have in terms of the evolution of the rampart mode. So it's rising. You can see it's rising. Most of the rising is happens during the first moment of the deformation, and then it's rising slower, and the stress is moving to the front this time. Again, most of the stress relaxation and the rampart evolution happens in the early stage of the deformation, and the stress position also tends to move closer to the front. So it's a smaller stress, but it changes also closer to the front. And the important point here is that, okay, this is for -15 temperature of ice, but what we can see is that on the center panel is that the time to maximal rampart mode will just be longer, so more. Cooler is your ice, less so colder. When your ice gets colder, the time you need to get to your maximum deformation takes just longer, but you get exactly the same shape in the end, and the same kind of distribution over time. It's just like takes longer, and this is shown in the right panel where we compare the different shape of viscous model depending on temperature. So actually what you can see on the right, on the B and C panel on the right, it's 20 curves that are perfectly stacked. So it's just like the temperature with 20 different temperature. So it's exactly the same result. So it doesn't really matter, except that for cold ice, the development of the rampart will take longer. So just more or less to conclude on the difference between elastic and viscous, here you can see that for different lengths of foot, so the foot under the water, longer is the foot, bigger is the foot, more important will be the frontal elevation, so bigger will be the rampart, and the stress distribution will go closer to the front. So it means that when you have a big foot, the calving event will actually be smaller. But of course, everything happens over time, so it's still a complex system to solve when you really want to predict where the ice will calve. And the results of our simulation is that the viscous and the 1D and the 2D elastic models, they really are quite well. And then the viscous model, it works a bit differently. So basically, most of the time, the maximum stress position largely decrease when the length of the foot increase in the viscous model, which is not as much the case in the elastic model. So okay, but such a low Young modulus, yes, I used the 10 megapascal. If you saw a 10 megapascal modulus of ice, it's very small. So is it realistic to use this? And because you see that the 1D elastic model and the 2D elastic model works pretty well, and they agree, but in both cases we use a non-realistic Young modulus. Actually, the Young modulus of ice is about 10 gigapascal. So we explain this small Young modulus by the presence of crevasses in the ice shelf. If you have at the bottom you have a lot of crevasses, then you reduce your effective thickness of the ice shelf. And this means that the ice shelf will bend more and will be less stiff. And so if you use, it's just like the Young modulus, the low Young modulus we use actually represents the presence of a crevasse. So here we simulated the real crevasses, which we didn't in the previous simulations. And you can see that when we compare the 1D elastic shape and the 2D elastic shape, we have a similar distribution of stress, and we have also a similar shape of rampart modes. So yes, reducing the elastic model in our simulations is a way to represent the presence of basal crevasse. Again, it's not enough yet to get to 10 megapascal, but there are other effects like ice softening and because of water content, and the fact that the crevasse are like can be also even larger. You have also stress concentration in the crevasse that can help calving even more. So so crevasses are important here to get our model to work. And yes, so just to hand viscous model and elastic model, the big difference is the strain rate increase with fluidity in the viscous model. So if you have an ice more fluid, the ice will change faster. The rampart will create faster. While in the elastic model, it's just instantaneous. And the maximum stress shifts to the front as the protrusion increase in the viscous model, while it's more stable in the elastic model. And longer the foot for a given rampart shape, and shorter the foot for a given rampart shape in the elastic model will give different calving rates. So in the end, we will have for a viscous model smaller calving events, and for the elastic model larger calving events. And yes, so I don't want to enter more into the details here, but what we saw as stress in the ice is about 0.1 to 0.3 megapascal, so it's not enough to calve ice. But again, when you think about the bottom crevasses in the ice shelf, then maybe we are able to create some calving events. So in the end, the study showed that viscous and elastic models give different results. And people most of the time in ice sheet modeling, they use viscous model. So maybe we need to use viscoelastic model to make the entire system works and being more realistic. The problem is that most of the state-of-the-art models right now, they don't use viscoelastic framework. It's only viscous, as I said. So we have to go forward with this. Maybe not for every problem, because it's viscoelastic simulations also bring other complexities in the system, but it's something we have to think about in the future. And actually, some papers from the last decades, they work more and more on that. Here you have a different example of people using elastic models or viscoelastic models for tidal deformation, for calving, and so on. So yes, I think our conclusion aligns well with what people are also working on right now. So thank you.
Thank you, Cyrille. That was amazing. We have plenty of time for questions. So yeah, if you would like to ask a question, you can either use the raise hand feature and I'll call on you, or you can just unmute yourself and ask Cyrille a question. Jinzo, do you want to go first?
Yeah. Oh, thank you for the great talk. I have a question, a very basic question about the steel, because I'm not a glacier person. So you mentioned there is a difference between ice shelf and sea ice, and what that difference? What is that difference?
Okay. Yeah. Sorry. So if we take maybe a figure here, it's not exactly sea ice, but so you have the ice shelf here, and at the front of the ice shelf here is icebergs, but after here you can see that the sea ice, you know, it's ice that creates on the water because of the temperature, you know, like cold water creates like change into ice, right? So it's sea ice is like surrounding Antarctica, and it's changing over time. So in summer and winter, you don't have the same concentration in sea ice, and some work show, or at least assume that sea ice could have an impact on ice shelf flow. But in our case, at least for a ice shelf, it didn't really make sense when we looked at the data.
Okay, so I guess sea ice is also typically much thinner than ice shelf, right?
Yes. So when you look at the ice shelf here, you can see it in kind of on the sketch. Here you have, like, I don't know, like for a ice shelf, it's 40 meters of front at least you're talking about, and for sea ice it's a layer of 1 to 2 meters at most. Yeah. So it's really a different thickness. So it's also hard to think that such a small thickness could you know, act on such a thick ice shelf.
Gotcha. Thank you.
Thank you.
Steve.
Yeah, lovely talk. Why can't you measure the dimensions of the foot? Is it simply too dangerous to get that close to the carving front?
Excuse me, can you repeat?
Why don't you have measurements on the geometry of the foot? Is it just too dangerous to get that close to the carving front?
Yes. So the problem is that most altimetry methods, they can't really see beneath the water, underwater, you know. So and yes, it's also something very hard to. It's a location you don't get to very easily to make such measurements if you want to do in situ measurements. But I think with ISAT2 there is a good chance, because ISAT2 is able to go, you know, a bit into the water, and Helen groups they work on that. I think you could see the foot maybe with some chance with ISAT2, but with regular measurements you're not really able to do that with satellite measurements in general, and in situ measurements are quite hard in Antarctica, at least because of the presence of sea ice and the risk with the icebergs calving. You know, I think it's a risky place to measure. But I just heard from a friend that they also have some foot observations and some measurements of the front for some Patagonian glacier, and it's the Japanese. They made these measurements in Patagonia, and they really can see similar shapes. And again, they link it to the fact that the surface water is warmer, so you leave the foot under the water.
Yeah, I would have thought you could do something with acoustic methods in a robotic boat.
Okay, I'm definitely not an expert in that, but yeah, I mean, I think there are ways, but here I think it's a LiDAR. You know, they use beneath under the water. Yeah, there are like different techniques you could think about, but I think the main problem is in general the risk in Antarctica when you want to do such measurements.
So I have a question, Cyrille. If you were to project what you think the implications of moving from viscous modeling to viscoelastic modeling might be on, for example, our estimates of the rate of loss of Antarctic ice or other important factors, what, if you had to speculate, what effect do you think, including the elastic effects, might have on these projections?
Yeah, it's tricky. I don't know if I want to answer that because I would probably be wrong. Yeah, so the point here was really to show, because people have used elastic models and viscous model to treat similar problems, was to show the difference. I think like what you really need is the viscoelastic model, as you said, and then see what happens, because we entangle, you know, we took like two extremes, viscous and elastic, and we looked at the difference. But no, I think it's time maybe to look at a proper viscoelastic model and see what happens when you put those two extremes together. And yeah, I think it's pretty hard to give you an answer on that. I don't want to risk anything.
That's fair. That's totally fair. Sushil.
So, Cyrille. Yeah, so I had a question about if you had a satellite mission that you were planning, what do you think you would need in terms of measurements to like improve your, I guess, modeling studies at maybe both the ice front and for kind of the sea level change, yeah, or sea surface change stuff?
Yeah, I think that for sea, and I think we discussed that together. I think like for sea surface 8, I don't know what kind of, because we are having like, you know, better and better measurements, and the time span between each track is getting smaller and smaller. So it's good to know the evolution of the system below, you know, a year time. But the uncertainty linked to melt and I guess firm compaction, all the uncertainty that makes your life hard when you want to know what's happening in terms of sea surface 8 beneath the ice shelf. I guess they remain, but you know better about that than me. So I'm not sure I could say what I want as a satellite mission for this kind of problem.
Can I ask a question? I don't know if you can hear me. My name's George.
Yeah.
Okay. Do any of your results affect what we talk about as the buttressing by the ice shelves on the glaciers, particularly from East Antarctica? I mean, where it's kilometers of thickness of ice. And that's really where the global warming problems are going to involve into sea level change. If that buttressing should reduce or be eliminated. So do any of your measurements have anything to do with addressing that aspect?
So here I look at very small changes because Ross Ice Shelf is not changing that much. I don't work directly on that, but people work a lot on buttressing effects. And yes, if thick ice has to disappear with thick ice with a strong potential and a strong buttressing, if it has to disappear in the future, then it would lead to strong changes in the ice sheet and the ice flow. And yes, there is like some theories about the fact that if you lose this portion of ice which have a kilometer thick, which are a kilometer thick, then it could lead to some strong collapse and very catastrophic scenarios. But so far, those theories haven't been proved, but it's a scenario people are considering. I don't know if it answers to your question.
Well, the only thing I've heard that I didn't realize is you call it the sea level change under the ice shelf from winter to summer. And I presume that's only on the order of meters. Is that correct?
Oh, even less. It's actually a few centimeters, but it's enough to tilt the ice shelf. So only a few centimeters is enough to change the flow. And again, the ice flow, so if I take a figure here, excuse me, here. So here at the front, the velocity of the ice is about 1,000 meters per year. And what we look at in terms of velocity change, it's about a few meters. So it's 1% of change we are looking at and we are trying to explain. So it could be seen as a very small effect with respect to what's happening in other ice shelf, like the West Antarctica, where we are looking at very fast changing ice flow. So yeah, here it's a completely different thing we are talking about, and sea surface 8 will never really be higher than this, I guess. So this scenario will never really matter more than a few meters per year of velocity change. So it's not an explanation or not directly related to the strong changes people are working on when we want to see and know what will happen in the future of Antarctica.
Thank you.
Thank you.
Are there any other questions for Cyrille? If not, let's thank Cyrille once again for presenting his research to us, and wish him the best in his future at Grenoble. And thank you for attending.
Thank you for the invitation. Yeah, it was great to be with you today. Thank you.